Welcome to Future Talk. On today's program, we're going to talk about computer vision. In order for modern robots to perform complicated tasks, they have to be able to see what they're doing. And that's where computer vision comes in. My guest is Gary Bradski, a leading pioneer in computer vision. Gary is founder and CEO of the Open Source Vision Foundation, which includes, among other things, the world's most popular library of computer vision software, an open source autonomous driving simulator, and a deep learning group that educates and advocates for artificial intelligence. Gary was also head of the computer vision team for Stanley, the early prototype driverless car that won the 2005 DARPA Grand Challenge and which now sits in the Smithsonian Institution. Gary, welcome to the program.
Thanks, Marty.
Gary, when we talk about computer vision, is that like human vision? Is human eyesight similar to the way computers see, or is it totally different?
It's probably quite different than what humans see. Basically, your eyes are very active elements, and there's all kinds of optical illusions and other things you can go explore that computers don't necessarily have. They have other things. In computer vision, we're taking a camera. There's a bunch of sensors, often colored with filters, red, green, and blue. And they're transducing that. Basically, computer vision is trying to turn what's the light that's coming into the camera into something that's meaningful information for something else to act on, whether that's sorting parts, counting cells, or driving a robot.
Now, can a computer look at the entire picture the way a human does, or does it have to examine each pixel at a time and calculate where that pixel fits into the big picture?
So, although there's now these things called deep neural networks that are maybe doing a little more processing that's like a human eye, what a computer does is very different. For one thing, it can pay attention to much more of the scene than a human does. Typically, it's surprising how little humans actually pay attention to because it's expensive to compute these things. Versus a computer often examines the whole scene and everything in it. Humans rely a lot on attention to direct focus.
Often, a human's attention will go to one particular thing in the picture, and they'll be oblivious to everything else. That's how a magician does it, directing your attention. Is the computer not susceptible to that?
People are putting in attentional systems in some robots and other tasks to try to make the processing quicker or more responsive or focal. But generally, the computer can analyze the whole image, and you just add more computer power. So it really isn't. Humans do this thing if you want, and you can remember to look up change blindness. So not only when we look at something, but that thing can change and we don't even notice it. Basically, we're cued to attention signals, and this change blindness is a trick in playback where they trick your attention signals by putting a gray frame between each frame, and so your motion attention system is shut down, and then you can play all kinds of tricks like change this into a flower pot, and you often just don't notice it.
So the computers don't have that sort of psychological stuff. They're not projecting anything onto it. But after it takes the picture, where does that information go and what's done with it?
So when the picture is captured, it's often, there's a fair amount of processing that happens in the camera to balance out the color and other things like that. And then it's often compressed so that the transmission doesn't take too much bandwidth into something like things called JPEG or motion JPEG. But then it gets in the computer, and then it's often decompressed. And so you have something that's mostly like what the camera received. It can process in different color spaces. So we think about our red, green, and blue, but often the image is represented in chrominance, so a color vector, and luminance, how bright it is, separate components. And then it goes through a series of algorithms depending on what the goal of the computer vision is. But it might look for features by processing with a sequentially more complex filters. It might be looking for motion vectors over a sequence of images. So
now you're head of something called Opencv, which is part of your newer organization,
right.
the Open Source Vision Foundation. And that, I understand, is the largest and most popular collection of computer vision software in the world. So, so what does that software do, and how is it used? Who uses that software? It's all free, right? Open source?
Yes. So I started this a long time ago with Opencv, the open source computer vision library. And recently we've expanded it to more general open source vision foundation to incorporate advances in AI, 3D vision, there's a lot of active sensing going, and also autonomous driving, which is a huge area of vision. So we've expanded this foundation and aimed it more at educational. But basically, at the bottom of it are these open source libraries that you could go right now and download for free and use them commercially for free. So the original intent was to couple of intents. One was to advance the field by giving people a lot of infrastructure to build on, but also to make, to do computer science, vision science, by having things repeatable. Before I started, people would write their own code, invent their own things. You could never repeat what they did. And here we just made the building blocks structured. So when someone did something, I was much more likely to be able to understand it in terms of its components and reproduce it.
So it's open source, which means that you have this collection of software, but anybody can copy it and modify it and add their own new features.
Yes.
Now, do those features ever get back into your original source?
So we have a lot of active contributors. Like, sure, if they contribute it back. And then we have a filter, so we have two different places, but in the main library, it has to be accepted. We have to say, well, that's important enough that everybody wants to use it, that it'll be accepted back in, not just every thesis or whatever that's done. I mean, most of them aren't really used. But we have another contrib section where if you want to put something there and maintain it, then you can. And that doesn't really have a big filter on it. Other than to check things in, everything has to be in a certain format with test programs and other things so that the code stays maintainable.
Now, when people download this software, do they download an entire package of software, or just maybe a few routines that they happen to need? Is the whole thing an integral, coherent package that you use as a unit?
So there's different things under the library. There's Open3D, Opencv, Carla is the driving. And Opencv is divided into modules. So you would allow the core module always that has the data structures and the basic algorithms. And then you can add more and more modules. But it's not all that big given today's computers, that you'd probably just download most of the core and then you could do the contrib. And it's still not, it's large, but it's not overwhelmingly large. This is code, so it's not images and whatever. So you'll have many megabytes, but not gigabytes. And so then generally you'll pick and choose. Now, if you wanted to deploy this on a cell phone, you would probably just link to the things you want and only deploy that.
Now, is there a lot of active development in this field? Because it seems like this is a pretty busy field because there's a big demand. There's a lot of development work in robotics, and robots need to see. So is this one of those fields that you're really encouraging young programmers to get into, because this is really the future of robotics?
Right. So, I mean, the field of vision is huge and growing. Way back in the beginning, more than 20 years ago, I used to feel a little guilty about, because it was fun stuff to program, but I thought, these people will never find a job because it doesn't work. Well, it turns out whoever started with computer vision has never experienced the recession. There's always been a growing demand, and these people are in top demand. So a lot of what we're doing in the foundation now is producing courseware, which is coming online, and more of it will come. that teaches you how to do this, and we'd like to formalize that into certifying people as a developer, which we think would make them very attractive to a job market. And we're also going to put on a conference, you know, it's a general educational and industrial theme. So we have growing activities in the educational area.
Well, I understand that you do have activities to educate and promote this type of software. Now, who is that aimed at? Is it aimed at potential customers who might ultimately buy stuff? Because you basically give it away for nothing. Or is it to encourage programmers to get into the field? Who is the target of this education?
The target is really, I guess, several areas. One is, well, it's programmers primarily. So we have these library routines that do certain functionalities that they can call. And so we have courseware that teaches them about what you can do and how you can call this. But it's also, many people just use computer vision now. There's artists, like these interactive artists in Barcelona, who use this so that they can make interactive art with a camera tracking. They don't really care much about how it works. They just call some higher level routine. They want to track a hand or a face or whatever. So there is a lot of that. And even in robotics, like I've seen it be used more and more in FIRST robotics. These are high school students. They're not experts, but I've seen them be able to track a box, count boxes, know the orientation of boxes for their robots to pick up. So, you know, on up to professionals who may know all this stuff. They could probably code the algorithms themselves, but it's not worth their time. They're working at a higher level. They just want these working routines that they can build on.
Now, if you use them in robots, does the robot have to be pre-designed to be compatible, because different companies develop robots? So doesn't software have to be compatible with the hardware that it's installed on?
Well, it's mostly, this is interpreting images. So those have been fairly standardized, that you'll get some sort of, again, transducing these incoming light into something that's meaningful. For instance, where's the thing I'm going to pick up? So there is this thing to translate, but that's more in terms of hardware and control. So I get a signal that I have to register within the coordinate system of the robot that says there's a glass there. Well, someone has to know that coordinate system and be able to move the hand there, and I can monitor it. But most of that processing is inside the library is the image, not the other code that needs to move the robot. So they'd have that specialized code mostly involves the robot and its particular setup, where the cameras are placed, what type of cameras. And
so what are some of the new features you want to add that you don't have now? What's the next step in this type of computer vision?
So this thing called deep learning, it's a form of AI that is loosely based on how people think the eye works, at least from its feed-forward, you know, vision to the brain path. That basically, it's called layered representation. So you have simple things like edges, and then groups of edges, and then groups of edges, as forming an image. And this has been very successful. So the next things we have, well, first of all, there's more and more capability with these. We're able to take an image and make it look like a painting, and take a painting and make it look like an image. You can find objects, track objects, infer from a 2D image what's the 3D. So it's getting a lot more powerful, and what we're tending to do is package more and more of that into something you can just use. You know, so routines, for instance, I was just at a company that just wanted facial landmarks to do a makeup kind of application. So they just called it. It worked. It tracked the face, and then relative to where things were on the face, they applied their other algorithms.
So a lot of the software is pretty specialized for very specialized uses, it sounds like.
So it's a mix of general and specific. The more naive users will want higher level functionality, like find the face. A lower level, I mean, the more advanced people in company, they often want the simple primitives. They, they're optimizing code. They just want something that'll find edges quick as part of a larger algorithm. So it's a mix, and the library has a mix and different levels.
Is there a risk of moving into sort of a surveillance state where the government sets up cameras at every big gathering point and identifies every person at that gathering?
So there is a risk, and hence this is open source. So one of the things is you at least know what's in there and what's not in there, and in a sense, you have as much power as the government to surveil them back. And also to argue about, not only to learn, how these things work, but then with the learning to argue back about what should and shouldn't be. Again, it is a tool, and like a hammer can be used as a weapon or to build a house. There's no getting around that.
Can these machines see outside of the range of human vision? So, for example, infrared, ultraviolet, could these see part of the spectrum that is outside what we call the visible spectrum?
Sure, that depends on the camera. So most people are familiar with the color camera, that it's just a regular sensor with some micro color filters, red, green, and blue filters on it. But you can do much more. First of all, most cameras see somewhat into the infrared, which is like the heat spectrum that's invisible to us. And specialized camera can see more and more into the actual heat. So all those are just what we call channels. So red, green, and blue are the first three channels. But you might have depth, X, Y, and Z channels. And you might have, say, heat, or near heat, middle heat, high heat. You might have X-rays. So this is called like hyperspectral imaging, the more and more information. Often those are for specialized applications like satellite imagery, analyzing what's happening to crops or...
Let's talk a little bit about autonomous cars, because this is one of the most important applications for computer vision and one of the most dangerous things if you get it wrong. What are some of the technical problems that you have to solve before you can let your car run on computer vision?
It's kind of interesting for us that I like you mentioned, helped out at Stanley, the car that won the DARPA Grand Challenge robot race across the desert.
And that was 13 years ago. That's
yes.
already obsolete.
Yeah, sure, but it helped kick off this whole autonomous driving industry. And Google literally bought that team. And that became Google Maps, and then the Google robot, which is now called Waymo. But that Waymo hive is literally a half a mile from my house, so I see these robots every day, like people elsewhere might not, and I just have become almost oblivious, like robots. Every day I bike and I pass or am passed by robots. But the challenges of those cars are, with the advances in computer vision, it's not that hard to drive, basically. You get a camera, you train it, it watches how you react, and these deep nets and other processing can learn pretty well. The hard part is those, it's like anything else. The first 90% is easy, and that gets people and maybe venture capitalists overexcited. Oh, we can do autonomous driving with a group of 3 people or whatever. And then they hit the 90%, and the rest is these corner cases that Google has been working on those 13 years. It's
like
just
unusual road conditions.
Unusual weather, unusual road condition. What do you do when a light goes out? What do a bag blowing across the street? Well, to the sensors, what's the difference between a bag and a rock? You might not know, and should you be slamming on the brakes when a paper bag blows by? Human wouldn't. So there are like many corner cases. Some roads, the lanes go off, or the road has been changed, and a human will reason that, oh, we go straight even though the lanes, the drawings have curved, and construction sites can change things or hide lanes. So these are what we call the corner cases. They're the fairly unusual. Per mile driven, it doesn't happen, but actually they're not, even if it's like like 1/4% of the time, you're going to hit that multiple times during a drive. So,
but what if it's a human directing traffic? There's a construction site, and he says, you have to stop now because there's a cement truck going across the road.
Right. So one of the reasons I created this larger foundation is because inside of it is Carla. It's an open source driving simulator, and I am a big advocate for the keys to driving have to be open, so that anything that's learned by any car can be shared and should be shared. Because companies have their proprietary interests, but I have an interest in keeping my kids alive, right? That trumps, I don't have to say the word, but their interest in making money by advantaging certain things that they've learned. Like everything that a car sees should be shared with all cars so that everything gets safer. But it's also, by doing this, having an open source base, it would foist a standard, say, the sensors that are in a car, they don't have to be in a car. They can be at an intersection or at the construction site. And I can transmit to a car a mile away, here's what you're gonna, here's a construction site, the roads have changed. I can draw on that, like the map, you're gonna go right and left to get around this, and they can understand there'll be a human there. This can be put on the map that's going to be directing. So now look for him, and here's the directions you'll get, when to stop, when to go. And so all that can be made safer if there's this shared infrastructure. So I want to build up the foundation to actually go around to Waymo and these other things and say, look, you have to start using this voluntarily and start making these standards, or legislation is going to come eventually. And that might not be favorable to the industry, so you might as well preempt that and be safer and just create these standards now. And here, everything's going to be fair because this chunk of code is open. Anyone can go, anyone can contribute, anyone can see what's in there.
So does that mean that all the driverless cars will be tied together into a network? So each car doesn't have to learn from its own experience.
Yes.
It learns from the experience. And if two driverless cars approach the same intersection at the same time, could they agree among themselves who goes first?
Yeah, so that's part of the traffic rules, but everything that a car experiences, anomalous or accidents, that should be shared so that every car can learn on it. But also by having the standard, for instance, at an intersection where let's say it's a 4-lane street and one car is stopped there, and maybe there's an old lady or a kid crossing in front of it. Well, even with the good sensors on this new robot approaching that car, it's still hiding this old lady or a young kid. And so that makes a dangerous situation as it comes to the intersection. It may think it can go, and yet hidden there is someone who's crossing. Well, if we could share the sensors, this car could broadcast, I'm stopped because there is someone in front of me, you can't see them. And so I think that's fundamental, that the sensing, and the intersection itself can help with that by putting up the same sort of sensors. So I think it's fundamental for getting this industry off the ground that these cars transmit local information.
Now, is safety the most important thing? So a car will stop, right? Like if somebody just walks in front of your car and they just stand there just because they feel like showing that they can bring this driverless car to a halt, what do you do about someone just trying to sabotage it?
I mean, to some extent, they can do that to you now, and sometimes it happens. I mean, they'll have to develop a protocol of honking or messaging or just calling the police after a certain time. So you can always vandalize stuff. What happens if someone's throwing black paint at a car? Well, they can do that to your car, and you would stop and call the police. And so I think the cars have to do that too.
Now, another question, these cars can see, but can they also hear? Do they know if somebody is honking at them? Can they hear tires squealing in the distance?
They certainly should. It's another sensing modality. And they should be aware of sounds. It can reveal hidden objects.
But so far they're not.
Well, I don't know what Waymo has in their car, but also inside the engine you might want to have something that's listening, and sounds can become anomalous, and the car is going to break or a belt is bad. So it can do that too. I think the car should have all these kinds of sensor systems, and I think they'll become far safer than humans eventually. And eventually, you might need a special license if you want to drive yourself.
Now, the driverless cars have the camera on top, and it's always spinning around in a circle. We see a lot of these cars here in Palo Alto all the time.
Yeah.
So why is it spinning around in a circle?
So those are the cars that are using something called Lidar. It's a laser range finding imaging. And not all cars do this, but most of them have some kind of Lidar, and not all Lidar spin. But basically, it's taking Lidar, it's a laser that it's timing how long, it sends out a pulse and it times how long it takes to get back, divided by the speed of light, and you have a distance measure. And it might have up to 32 right now of such sensors. And they're all in one plane, so they spin. And they just do this. It spins like, 30, 60 times a second. Everything's happening very fast. And so it builds up a whole image of the complete 360 around the car of what's happening in depth. A lot of these are aligned with a small camera, so it creates an image that has red, green, blue, and then the depth values, like how far that pixel was in the scene.
We're almost out of time, so this will have to be the last question. How soon do you think it'll be before the average person in the public can buy a driverless car?
I think you'll probably, maybe never buy it. Everything will turn to kind of driverless Uber. There's no reason to have a car if you can just whistle and one comes, right? You don't need to waste all that space in your house to store a car. These things, once they let you off, they drive off somewhere else to get the next person.
Okay, we're going to have to stop there because we've gotten the signal. Great conversation.
Yes.
I've been talking to Gary Bradski about computer vision. Visit our website, www.futuretalk.com. For Future Talk, I'm Marty Wasserman, and we'll see you next time.